Hello, Pamela. Oh, I can't hear you.
I have to unmute myself.
Okay. We just did this!
I know, but I'm being distracted by this absolutely fabulous moonrise combined with an absolutely fabulous sunset. And I'm going to share a picture I took real fast. And while it's being shared, I can still talk, but I'm going to set up my camera to take a couple pictures. So that is what's going on right now here in Lisbon, where we are, I think, 2 hours past supermoon. Um, which was the Earth being as close as it gets to the moon, or the moon being as
Yeah,
close as
that's
it
a
gets
strange
to
way
the
for you to
Earth.
describe it. It's all relative, sure. Yeah,
Both are true. Both are
both are
true.
true. Yeah.
Um, and it is conveniently happening just about the same time that we have moonrise here in Lisbon. So I will pass you the planet in a little while, but for now, I've got all the beautiful things, and the moon is totally in the clouds now.
That's fun.
Ah, fail.
Wow.
But I can see all of the sunset reflected out on the inlet that Lisbon is on, and there's just beautiful clouds everywhere. So I am
I,
talking.
I can hear you taking pictures right now.
Yeah, it happens. Deal. Anyways, we can do astronomy cast while I share pictures and take pictures because we're talking about acceleration and life is accelerating as we speak.
Nice
You're
segue.
ignoring me.
Nice segue.
Yeah,
No, no.
well, I try. Okay,
Um,
I'm heading back to my desk.
all right. Can you share your pictures while we talk before we
Yeah.
start? All right.
Hmm.
So if anyone has no idea what it is that they've stumbled into, you're watching a live episode of Astronomy Cast, our weekly podcast about space and astronomy. We're going to be recording episode 314 at an unusual time. Normally, we record these Monday at noon Pacific, 3 o'clock Eastern, and who knows what time in Portugal. Um,
8 p.m.
8 p.m. Portugal time. Uh, just 100 hours Portugal time. And so it takes us about 20 minutes to record the show, 22 minutes to record the show, and then we wrap that up and we stick around for a few minutes and answer questions. And I know Pamela is hungry, and we'll be looking to answer quick questions that allow her to get to her food at some point. So don't be surprised if we have to kind of wrap this up quickly. So there's a bunch of places you can ask some questions. One is over on the event page on Google+. Another place is just on YouTube, and to be honest, YouTube is the safe place. So if you're just watching this video anywhere and you're feeling the need to make some comments, just click on Watch on YouTube, and then when it pops up on YouTube, you should see where all the comments are happening, and you can post your comments in there, and we'll absolutely get those. I can't guarantee any of the others. So, okay.
I am trying to unscreen share. There, I succeeded. So
Okay,
I now have the lights behind me,
just how
but
we
I can
like them.
quickly whip around and take pictures.
Okay.
I will
All
try
right.
not to.
All right. I'm just thinking, record a show, focus on the show.
Okay, we
So I'm
can record a
thinking
show. I will pretend to focus on the show.
we could wait. You're
No,
the
it's
one. You're the
good.
one that's
It's
hungry. No,
good. I
no,
want
no.
to eat
Let's wait.
dinner.
No. Why
So,
don't we
no,
just
let's
wait? We'll just
record.
wait till you're done.
No, we can
All
go.
right.
Sorry, I
All
hope I'm
right.
amusing all of you.
Okay. Yeah. I'm ready to record.
I'm ready as well.
Okay. I'm gonna press record. I just pressed record.
I lost GarageBand. Hold on. Too many windows. I'm sorry. I suck. It's
Say when.
working on it. It's there it is.
Is it recording?
I am pressing record. It is recording episode 314 in stereo stopping.
Okay. I will start again. No problem.
It's it's
Don't worry about
set
it.
to mono. How are you set to mono and recording in stereo? That is so confusing. Pressing record. Okay, now it actually agrees with me that it's mono.
Perfect.
I didn't change anything. It's possessed, but all right. Okay.
Okay. Here we go. Astronomy Cast, episode 314 for Monday, July 8th, 2013. Acceleration. Welcome to Astronomy Cast, our weekly facts-based journey through the cosmos, where we help you understand not only what we know, but how we know what we know. My name
Hello.
is Fraser Kane. I'm the publisher of Universe Today, and with me is Dr. Pamela Gay, a professor at Southern Illinois University at Edwardsville. I'm going to start again.
Hello.
Are we losing you?
You.
Can you hear Pamela? Uh-oh.
Okay, you're now there. I'm going to try and move closer to the router. Can you hear me?
Mm-hmm.
Okay.
So is that what happened? You were far away from the router? That's okay.
I don't think so. I think it's because everyone's now home. But I'm now close.
Can you jack
I'm now
right
closer
into the
to the router.
Okay.
No.
Okay. Should we try that again? It's okay. I totally messed up the intro, so we're good. Oh, wah wah. And this is the point where I have to entertain people, I guess. We'll just wait for Pamela to get back. There she is.
Sorry. Okay. I should probably start GarageBand over, shouldn't I?
I don't know.
Preston, we love you. We're sorry. I'm going to keep my audio going.
Oh, I cut my audio.
Oh, then I will stop and go
let's
back
start
to
again.
the beginning.
Yeah, please.
Okay.
We don't hate him that much.
No, that's true. We don't. Okay, I'm pressing record again. And it's recording in mono.
Good. Okay. Let's try this again. Ready?
Mm-hmm.
Okay. Astronomy Cast, episode 314 for Monday, July 8th, 2013. Acceleration. Welcome to Astronomy Cast, our weekly facts-based journey through the cosmos, where we help you understand not only what we know, but how we know what we know. My name is Fraser Kane. I'm the publisher of Universe Today, and with me is Dr. Pamela Gay, a professor at Southern Illinois University, Edwardsville, and the director of CosmoQuest. Hey, Pamela, how you doing?
I'm doing well. How are you doing, Fraser?
Good. I am enunciating very carefully after messing up the first intro, and we had a few technical problems getting this episode rolling. So now I'm walking on pins and needles. Hey, have you seen the trailer for the new Cosmos show yet?
No.
Our favorite person in the world, Neil deGrasse Tyson, is doing a recreation of Cosmos with Seth from the Family Guy, and it looks awesome. It really looks amazing, and I can't wait to see it. They ran the trailer at Comic-Con. It looks just phenomenal.
Yeah, I've been working my butt off over here, and I'm highly amused because Netflix keeps sending me emails reminding me that I have an account. Use it. And it's like, no.
That's sad.
So nothing it exists except for the work I'm doing right now.
Well, when this is over, go search for the new Cosmos trailer and watch it, and I think you'll be pleasantly impressed. The fact that it doesn't have enough Fraser and Pamela in it is a problem. Apart from that, it just looks amazing. It looks I'm so like it's on Fox. What a crazy time we live in. What's going on? That Fox is going to be showing this, science show with Neil deGrasse. I love it. I'm super excited. So, all right, let's get on with the show.
Okay.
So put that pedal to the metal and accelerate. It's not just velocity, but the change in velocity. Let's take a look at acceleration, how you measure it, and how Einstein changed our understanding of this exciting activity. So, Pamela, am I accelerating right now?
Yes.
Really?
Yes.
How?
You're on a planet that is rotating, and so your motion is constantly changing its direction. Our planet is also orbiting the sun, so your motion is constantly changing direction. And I'm fairly certain that since our planet's motion around the sun is a ellipse rather than a perfect circle, that even your speed relative to our motion along the orbit is varying. So you have both variations in speed and variations in direction, and if you change either one of those aspects, you have an acceleration.
Cool. Okay, so then I guess we're going to have to go into let's start with, I guess, my physics, my high school physics version of acceleration before we move into my university physics version of acceleration. So what is acceleration?
Acceleration is a change in velocity, and velocity is speed in a direction. So if you change something's speed, how fast it's moving relative to the surroundings, irregardless of direction, or if you change the direction that it's moving in your X, Y, Z three-dimensional reality, change either one of those factors and you have a velocity.
Have an acceleration.
Not a velocity, you have an acceleration.
And as you sort of mentioned at the beginning of the show there, that your acceleration, it's not just like I'm sitting in the car and I put the gas down and I can feel myself pushing back into the, into the seat as I move. If I'm
Yeah.
just going a constant velocity and I turn around a corner really quickly, I'm going to feel an acceleration.
And so there you have to be careful because it wasn't actually a constant velocity. It was a constant speed. Velocity is what's called a vector property. Vectors are things that have a magnitude, so they have a number saying how much they are, and they also have a direction. So velocity is a vector component because it has a direction that it's going in, and then it has a rate, a amount of distance over time that it's going. So it's
Right,
that
and that's a
combination of dx dt and the little vector hatted letter of what direction you're moving in.
right. And woe to the science writer who gets those two mixed up and writes it down and has to read the comments and apologize profusely. Not that that's ever happened to me.
No, never, never at all.
Right. So, right. Okay. So we got the situation, as you said, where your, I guess your speed doesn't change, but your velocity changes. Wait a second. Anyway, as you go around the
Yes,
corner,
yes.
you are getting that acceleration in a sideways direction because you're getting that change in velocity.
And here's where it starts to get really confusing because as your car goes around that corner, you feel yourself getting slammed outwards into the outer edge of the turn. So if I'm turning in this direction, I feel like my body's getting forced out. But the reality is the force is pointed inwards. That's why I move in that direction. And me getting flung against the door is because my body wants to keep going straight and the car has moved around me. And so it's my failure to move conveniently with the car that creates this fictional, non-existent force that makes it seem like I'm slamming into the door. The reality is the car moved, I have to catch up.
And this is where we go down another rabbit hole and talk about the difference between centripetal and centrifugal force. But we've done a whole show on that.
Yeah,
I feel like
yeah.
we've got that perfectly squared away, so I don't think we need to even talk about it anymore.
Okay.
Right. Okay. So this is my Newtonian comprehension of acceleration, and then we're presented with these these various formulae to calculate if I jump off a cliff, how long does it take me to
Yeah.
hit the water? If I throw a ball up into the air, how long does it take for the ball to come back down, etc.
So what
So
is the one thing that's always required in order to get an acceleration?
force.
Force. Force equals ma. Force
Right.
equals mass times acceleration. It is the one most important formula in all of physics. F equals ma.
And that was one of the things, I guess, in high school physics where I was quite intrigued, was just this concept of being in perfect balanced force. That, that I am standing on the ground and I'm pushing down the ground and the ground is pushing back. And
Yes.
if I didn't have that, then I would have acceleration.
Right. And so people always talk about their feet hurt because gravity is pulling them into the ground. But they can also turn that around and say their feet hurt because gravity is pulling the earth into their feet.
Poor, and
Both are
think about the
valid.
Earth. Think how
Both are
sore the feet.
valid.
Think how sore the Earth is from all these
The
feet.
surface.
Yeah, getting
Yeah.
pushed into it. It's not
Yeah.
fair. Um,
What, 6 billion
yeah,
feet?
right. So okay, yeah, and so the situation. So if you're not moving, then the forces on your body are in perfect balance.
Right. Now the catch is this is where you start getting into frames of reference.
Well, we just moved into the university physics, didn't we?
Yeah, it happens.
Okay, all
Sorry.
right. Well, it's okay. We can cross that bridge now. Let's go there.
Okay, so here I am. I'm in a room in Portugal. The sun has now set. It's no longer pretty outside. And I feel like, except when I decide to rotate in the chair, I feel like I'm perfectly stationary. But I'm not. I'm on a rotating, orbiting planet that's in a solar system that's whipping around the Milky Way, which is on its way to fall towards the Virgo cluster while it's also falling towards Andromeda. There's all these motions going on, and I'm part of all of them. But from my perspective, I'm in an inertial frame of reference where everything seems to be balanced out, and I can only measure things relative to my frame of reference. Kind of sucks.
Right. So now is my frame of reference pretty much the same as your frame of reference right now?
Um, no, because you and I are in different north-south positions on the planet Earth. We're different distances from the center of the planet. And so while you feel like you're experiencing nothing and I feel like I'm experiencing nothing, um, we are actually whipping around the center of the planet at two different velocities. And because we're different distances from the center of the planet, very minuscule because we're both pretty darn close to sea level right now. But because we're different distances from the center of the planet, we also are experiencing different gravitational pulls from the planet.
Right, the acceleration of gravity from the planet.
Yeah.
Right, okay, but I mean if I was on Mars, then I would see your acceleration differently, right?
If you were on Mars, we'd see our motion relative to one another. And so it becomes the problem of we're on planets that are both going around the sun, but they're going around the sun with the Earth moving faster than Mars. And I can't do that and keep my fingers on camera.
Right.
So we're on two planets that are orbiting the sun at different rates, at different distances, and so we do see motion relative to one another. You and I don't actually see motion relative to one another unless we start looking at plate tectonics, and that requires a whole lot of waiting I don't feel like doing. Um,
Right, but I guess what's very interesting about this is that as I see, as I'm on Mars and I watch you on Earth
yeah.
picking up speed and coming towards me, I'm seeing you accelerate. But from your perspective on Earth, you're not feeling that acceleration, even though it's
And
happening.
and this is where one of the things that Einstein came up with was the realization that no two observers ever observe the exact same thing. You and I are both experiencing the passage of time ever so slightly different. Um, if you put us on two different worlds, we see one another's motion as different. If we each assume the other one is if we each assume that we are stationary and the other one is moving. And so when it comes to trying to sort out simply the time of when something took place, no two observers will necessarily see the exact same time without doing all sorts of mental and computational arithmetic to sort out the differences in time generated due to relativistic effects and just light travel time. If you and I both observe, and I don't know if we can because I think we're actually 180 degrees apart right now. We're more. No, we're both on.
We're 8 hours. We're 8 hours apart,
We're
right? So
8 hours, so we're fine.
yeah, we're a
So you
third
and
of an
I
Earth
can
away from each other.
you and I can both observe the moon at the same time once it gets much higher in the sky. And so if we both were able to observe a meteor crashing into the edge of the moon and letting out a fireball to the side, this isn't going to happen tonight, I'm just saying a what if. If you and I both observed that same what if, because the distance from me to the moon and from you to the moon is different, we're going to end up seeing different timings for that event. And then when you take into consideration the amount of time that it takes a signal to reach from me to you and you to me, there's a whole lot of things that have to be taken into consideration. So you and I might both say, hey, I saw it, but we didn't see it at the same time.
Right. Now, so what was sort of this big change? the university level physics, the college level physics that Einstein had sort of come up with, right, about his sort of fundamental understanding of what acceleration is.
Well, so prior to that, we'd started to get from Galileo, because you do have to step back a little bit further. From Galileo, we'd gotten the idea that an object in motion tends to stay in motion, and an object at rest tends to stay at rest.
Newton?
He was No, Galileo actually came
Galileo.
up with.
Okay.
Yeah, yeah.
Okay.
So we have to step back to Galileo. So when you step back to Galileo, you get an object in motion stays in motion, an object at rest stays at rest. It was Galileo who figured out the concept of friction. Prior to that, it was an object in motion would come to rest. But then how do you explain the moon? How do you explain the stars? And Galileo was not pleased with the explanation of that's just the way it is. They're heavenly bodies. He wanted more reality. And he figured out friction. He figured out inclined planes, and that there's a similar amount of acceleration if something falls straight down or if it goes down all the way down to the bottom of an incline. You're changing the same amount of potential energy into kinetic energy no matter what route you take. And so Galileo put all of these initial ideas together, but beyond sorting out friction, he didn't get to the underlying concepts of you need to put the same amount of force on two different objects if they have the same mass and you want the same acceleration. So this is if you have a pound of feathers and you have a pound of lead, they're both going to fall at the same time, ignoring aerodynamics. The concept of mass gravitational acceleration equals a force. That came from Einstein. The next thing that came, not Einstein, came from Newton, Isaac Newton. The next thing that came from Isaac Newton was the concept that the moon is actually falling around the Earth, that it's a force that keeps it in place. This was very mysterious. We had Kepler's laws explaining the motions along ellipses. We had Galileo trying very hard to get at the concept of forces. And then we had to wait for Isaac Newton to get born and grow up and develop calculus and figure out that the moon is actually falling, but as it falls, it's able to miss the planet Earth, but it's constantly falling in an ellipse as it goes around. And he was able to work out and balance all the forces.
And, thanks Galileo. Thanks. Have you ever done that experiment where you like roll a bunch of
Oh,
cylinders?
I have not only done that experiment, I have forced students to do that experiment with water clocks like the one Galileo used.
Oh,
And
really?
yeah,
How
yeah.
well? And I guess that's the whole point, right? Is that the timing is terrible, so you want to slow down that whole process to use the inclined plane to kind of slow the whole system down.
You can actually get surprisingly accurate with a water clock, and everything gets measured in milliliters of water instead of in seconds of time.
What's your favorite experiment to do? Is that the one with the inclined plane to sort of demonstrate acceleration and gravity and things like that?
I don't know if that one's my favorite. I think my most satisfying one is actually a pendulum experiment where you suspend a ball bearing in a sling of saran wrap, pull it back and release it so that the saran wrap gets cut by a hot wire, and then the ball will go flying off and you can calculate exactly where it should land. And when I do this with students, I give them just a soup can and I say, okay, run the calculations, put the soup can where you think the ball bearing's going to land, and they're always shocked and amazed when it actually works.
That's really cool.
It's highly satisfying.
Back
Physics
back
at work with a thunk.
right, and it landing sort of where their math predicted it would land, which
Yeah.
is really neat. Yeah. So I guess the thing is that it's kind of mind-bending. We go back to sort of the Einstein concept of acceleration. When you think about that frame of reference, you know, in our in the classical understanding, these things are all true. That you're dropping this cylinder and it's rolling down a slope and it's landing at the bottom. But Einstein, I think, really kind of turned that all on its ear with his concept of these frames of reference and the fact that it's all relative. That from your perspective, maybe, but there are other perspectives out there that aren't seeing what you're seeing.
But the one neat thing that came out of it was things like the twin paradox. And the twin paradox gets defined by who's the poor sod that's getting accelerated through space. So the concept here is, and we've discussed this in depth in other shows, is the speed of light remains constant for all observers. So if you're moving, in order for you to perceive the speed of light of the flashlight you're holding in your hand as a constant, time has to slow down for you so that you aren't catching up to the waves and seeing light slow down. So if you have two observers and one stays on the planet Earth and the other one accelerates away from the planet Earth at high enough rates that time perceivably slows down, it's the one that does that accelerating that experiences the slowdown of time and the slowdown of age and eventually gets called Buck Rogers.
Right. That's it. They always have to change the name to Buck Rogers.
Always, yes.
Yeah, yeah. I loved that show. Right. And I mean the twin paradox. There was a really interesting. I'm trying to remember what I see so much of this stuff, but someone had just sort of just done the math about, if you did want to go and travel across the universe essentially, and if you could get yourself going fast enough that you could almost survive, like in a human lifespan for you, be like, whatever, 100 years, you could pretty much get completely across the universe from, if you're going fast enough from your perspective, and yet, billions and billions of years would have happened for the rest of the universe.
It's actually quite useful because there's particles called muons that are highly unstable and are formed when high energy particles hit our atmosphere. And because they're moving very fast, they're able to make it all the way to the surface of the planet to get detected. And what to them is a fraction of a second, but is a perceivable amount of time to us poor sods on the surface of the planet.
Now, what is it called where if the acceleration is changing? Have you heard, that?
It's called a change in acceleration.
So, I mean, there isn't like
it's the first derivative of acceleration.
Right. Yeah.
So all of these are derivatives in calculus. So the way to think of it is you have a position. Your change in position over your change in time is your velocity. Your change in position per second, so in per unit time, so every distance I go increases every interval of time. That's my acceleration. If I take another derivative of that, that's when I start to get the change in the rate of acceleration, which is another derivative.
Now I want to do a little mind experiment with you here. Let's imagine that you were inside an elevator. You're like,
yes.
10 stories up, and you're going down, and then the rope breaks,
yes.
and you fall to the ground, and
yes.
then just before you hit the ground, you jump up, and you avoid certain death.
No.
Now, am I fundamentally misunderstanding acceleration here? What's going on? Because I mean, people think this is the case, and obviously it's not the case. So what's wrong with that thought experiment?
As the elevator falls, you are now in a weightless environment where you and the elevator are both moving relative to gravity in free fall. And so, first of all, you can't really jump up because you're kind of hovering in the middle of the elevator, quite likely. And it's one of those horrible situations where first you get slammed into the top of the elevator and then you're in free fall. And then you die at the bottom with the sudden deceleration, which again slams you into the ceiling of the elevator.
Right. So I guess the point being that you're in free fall. You and the elevator are falling at the same speed. You are still falling that entire distance.
Yeah, and the elevator hits the ground first and begins its deceleration first, causing you to decelerate against it.
Right. So you would, well, I guess you would smash into the ground, second or milliseconds after the elevator starts, it's smashing into the ground. Yeah. And unless you could jump, unless the top of the elevator could pop open, and
Yeah,
you
but
could
then you're just gonna, you still have all of that potential energy to convert into
right,
crashing energy.
right. No, and you could jump the height of the building,
Yeah, no.
and you
Just
could
making
somehow
stuff
get
up
yourself
now.
down to the bottom of the
No,
elevator. If you could pull off those things, then you'd be safe.
no. No, so the whole problem is when you're 10 stories up, you have a certain amount of gravitational energy, gravitational potential energy. As you fall, all of that gets turned into kinetic energy. Under normal circumstances, the elevator transforms that potential energy into friction and other things that the elevator's absorbing, generating in the form of heat, sound, other stuff into the environment around it. Remove that dissipation of energy. As you fall, all your gravitational potential energy becomes kinetic energy. That kinetic energy has to get dissipated somehow when you and the elevator hit the ground. And it's going to end up turning into sound, deformation of the elevator, deformation of you,
Yeah,
generally things you don't want to experience.
right, right. It'll be a very bad day.
Yeah, it's conservation of energy. It's a problem.
All right. Well, so hopefully people can kind of take that back. Actually, MythBusters did a great experiment on it. They actually tried to test it and demonstrate that yes, it's ridiculous, and you're not going to help yourself at all. So
Death.
death. All you get is death.
Okay,
Okay, great. Well, thank you very much, Pamela.
my pleasure. Okay, you want to see the pretty pictures I took when I was being an airhead at the beginning of the episode?
Yeah. Let me just make sure I've got this saved.
Okay.
Okay. Let me just make sure it's uploading, and then go ahead and put your pictures up. Wow.
Yeah. So you see
You
why
didn't.
I had a moment of I'm going to take photos. It was just striking. And that lower band of orange, that's the ocean reflecting the clouds.
We've lost your picture. It's back to you.
Oh, okay. So apparently you can't go full screen. Um,
No.
okay. Am I now screen sharing?
No.
Oh, crud. Okay, let me try this again. There we go. Start screen sharing. Now can you see it?
Mm-hmm.
So this band of orange on the very bottom, that's actually the inlet reflecting the clouds. And so it was just absolutely stunning out there. So I very quickly dashed a whole bunch of pictures. And that's a castle. But yeah, it was beautiful out there. And then before that,
Uh,
go ahead.
oh, I was going to say someone. So I actually was a sort of a trick question in the episode. You know what the change of an acceleration is called?
What?
It's called a jerk.
Oh man,
Yeah, I'd set you up like a
I
beautiful
I
gift,
failed.
and yeah. So
But I have
yeah.
the
So
moon. I have pretty
so
pictures of the
you got
moon.
pretty pictures of the moon. Yeah. So thanks, Alex. Right? Yeah. It's jerk. Um, those are, let's go back to these. Oh, look at you, an airplane.
Yeah. I was in such a hurry to catch it, I missed flat, but yeah. And there I got a
Got a
bird.
bird. If you've good timing, if you just got a little, well, I probably would have missed.
Yeah, it missed. But yeah, it was so that one is kind of the piece de la resistance, the supermoon, and you can actually see the atmospheric noise in the picture.
Totally. And you
So
can see
yeah.
that it's super.
Yeah. Okay.
It's a super
I'm
picture.
done. I should go eat.
Okay. All right. Let me see if I got any questions here.
Okay.
Okay. So Michael Jobin says on the equator we can jump higher, and that is true. You can
Yeah,
jump
you're
higher at the
further from
equator.
the center of the earth.
Well, it's not just that. It's also you've got
Oh,
the
centripetal.
acceleration. Yeah, the sort of centripetal force that's pulling you outward. So I think you're like 1% lighter when you're at the equator. I forget. I did the math at one point.
Yeah, I never remember. I assign it as homework and redo it every time I teach the course.
How much weight do you lose when you travel from the North Pole to the equator? That's good. Not
You too can
much.
do these at home. Yeah.
Yeah. And then I've got, let's see, there's some other questions. Anything in event? Guido says, thanks for the link. No problem, Guido. It's just for you. Um, okay, cool. All right, well, I think that's it. One person
Okay.
mentioned deceleration, which we didn't discuss. We discussed acceleration, but not
It's the
deceleration.
same thing.
It is the same thing, yeah. Okay, awesome. All right, well, then, if we don't see you, have a great week, and maybe we'll see you on next Monday, if you can get some
Here's
internet.
hoping. Yeah, I don't know what the internet's going to be like in Greece, so we'll see.
Okay, all right. See you later. See everybody.
Okay.
Thanks for watching us. Bye.
Okay. Bye-bye. We are, I think, 2 hours past supermoon, um, which was the Earth being as close as it gets to the moon, or the moon being as
Yeah,
close as
that's
it
a
gets
strange
to
way
the
for you to
Earth.
describe it. It's all relative, sure. Yeah,
Both are true. Both are
both are
true.
true. Yeah.
Um, and it is conveniently happening just about the same time that we have moonrise here in Lisbon. So I will pass you the planet in a little while, but for now, I've got all the beautiful things, and the moon is totally in the clouds now.
That's funny.
Ah, fail.
Wow.
But I can see all of the sunset reflected out on the inlet that Lisbon is on, and there's just beautiful clouds everywhere. So I'm
I
talking.
I can hear you taking pictures right now.
Yeah, it happens. Deal. Anyways, we can do astronomy cast while I share pictures.
Hello, Pamela. Oh, I can't hear you.
I have to unmute myself.
Okay. We just did this!
I know, but I'm being distracted by this absolutely fabulous moonrise combined with an absolutely fabulous sunset. And I'm going to share a picture I took real fast. And while it's being shared, I can still talk, but I'm going to set up my camera to take a couple pictures. So that is what's going on right now here in Lisbon, where